So, in our discussion of waves with Huygens principle, we introduced the idea of interference. Now, I'm going to expand on that a little bit. So, imagine that we had two waves that were adding together in this fashion. Then, what would happen is you'd end up with a bigger wave. Whereas a wave like this added to that, they'd tend to cancel each other. And so, with constructive interference, you end up with a bigger wave. Destructive interference, you end up basically canceling. And so, this is an interesting sort of thing because we can actually utilize this. Now, let's look at an example radio transmission. So, you have a radio transmission. Imagine a radio station. And of course, the radio station has this big tower, and the tower stands up very tall, and the tower is it can be thousands of feet tall. And so the idea is that you broadcast and the signal goes a very long way because radio waves don't go through the earth. And so the taller the tower, then it can see over the curvature of the earth a little bit more. Now, for an AM transmission, then what happens is the signal kind of goes omnidirectionally away from the tower. Now, in that case, the signal does actually go upwards. There's nobody that lives up that way, but in the upper part of the atmosphere, the ionosphere can actually cause that to reflect downwards. And so sometimes it can reflect downwards, reflect off something on the ground, reflect back upwards, reflect downward again. Shortwave radio does this dramatically, and so that way that at different times of the day you can possibly hear here in the United States and here in Texas, you can actually hear radio stations in Europe or Asia or all over the place. Even AM radio does this sort of thing. And so that means that at night, when the ionosphere is at a different level, then and reflective capabilities are different, then what happens is at night that you can here in Texas hear radio stations in Nashville and Chicago and New York City and Los Angeles. There are certain radio stations around the country that have clear channel license, so they pay extra to have a license that no one else, no other AM channel and no other AM station in the country uses. And so at night, when the ionosphere is at higher level, then what happens is you get these reflections, and you can hear those stations anywhere in the country. Now, FM does not reflect off of the ionosphere in that fashion, so it's not beneficial for a signal, FM signal, to go omnidirectionally because no one lives above the tower, and generally no one lives below the tower either. So what you really want the signal to do is spread outwards from the top of the tower, not going up, not going down, because there's no one above it listening, no one below it listening. And so since conservation of energy, if you use the same power in a signal that's planar, going out, in a cone away from the top of the tower, mostly in a plane, then you actually have the same power over a smaller area because you don't have the full area of an omnidirectional signal. And so in that case, you have more intensity. Power over area is intensity. So how would you make a signal more directional like that? Well, let's consider one particular radio station. Okay, a radio station has a frequency of 98.9 megahertz. Okay, well, we know that the way waves work, C equals lambda F. Okay, so lambda, the wavelength, is C over F. Okay, so that would be 3 times 10 to the 8th meters per second divided by 98.9 times 10 to the 6th hertz. That comes out to be 3.03 meters. Okay. Well, think about destructive interference. So I've got a signal like that. So if I have two broadcasters right here, they're in sync. But if one of these is moved a little bit, so let's imagine that one is moved over here, okay, so that now what happens is So I move the broadcast maybe over to here somewhere. So now then it's shifted. Well, it's shifted so this peak there shift over to here. So basically what I've gone is half a wavelength. One wavelength would be peak to peak. So peak to trough is half a wavelength. And so a shift of half a wavelength would give you destructive interference. Okay, so if I were to have my tower here, so here's my radio tower. Now, a lot of people mistake that tower to be the antenna. Really, if you look at the tower, that's not the antenna. The antenna is this little thing that sticks off up here. Well, actually, you might have two of them right here. And they might be spaced here so that the height difference is half a wavelength. Well, that means that if they're half a wavelength difference, then signals that go off this way are all going to be in sync, and so signals going off this way are all in sync, and so you get constructive interference this way, but this way, then this one is completely out of sync. It's completely out of sync with the other one. Okay, so now they're destructive interference. So for the example we just did, where lambda was 3.03 meters, half a wavelength would be about 1.52 meters. Yes, 1.515, but that rounds to 1.52. So what you would do is you'd build your tower. And you'd put these antennae up here so that this vertical separation is half a wavelength or 1.52 meters. That way you get destructive interference up and down and constructive interference side to side. And so you'd have no power going up, no power going down, and all the power going off to the side. And so this would be an example of an interference pattern here. Now, really, to make it even more powerful, you'd probably have like a bank of them up here doing this sort of thing, all spaced half a wavelength apart. And so this gives you these interference patterns. And you can see the same thing in multiple other situations if you want to have a directional signal, is that you adjust it so that you get constructive interference in the direction you want the signal to go, and a destructive interference in the directions you don't want it to go. So there's multiple examples of this. This is just one possible example right here.